Okay, welcome to Chemistry 202. I think most of you are in here fresh from Chemistry 201 last quarter. Some of you may have taken Chem 201 the previous year or some other class. But we're going to start off with some of the logistics for today. And so let's talk about what's going on in organic reaction mechanisms too. So I'm your instructor, that's me, Dave Van Vranken, and your TA, Gene Gutman, is not here today. And you'll see Gene, I think, starting on Wednesday. And you had a whole selection of books. There is no perfect book for this class, just the same as in Organic Reaction Mechanisms 1 in Chemistry 201. I'm listing one book here that I think is important for this class, and that's Ian Fleming's Molecular Orbitals and Organic Chemical Reactions, and I think that was a book that you were familiarized with in the first quarter of this class. Hopefully you have a copy of that. Another book that's useful for this class is Carey and Sundberg's Advanced Organic Chemistry Part A. There's a Part B that's more oriented towards organic synthesis and how to do synthesis, but the Part A series is all about structure and mechanism. And you may have been familiarized with that book in the last quarter, may have a copy. There is an online version of the earlier 4th edition. And to me, the 4th edition actually is a little simpler and is actually a little better than the 5th edition. I have a copy of the 5th edition. The 4th edition is online, and I'll put a link to that on our course website, so you can access it from wherever you want, however you want. The grading is pretty similar to what you had in the last quarter. Most of your grade is going to be from midterm exams and from a final exam. So we've got 2 midterm exams, and the final exam is worth about really twice as much as the 2 midterms, and it's going to be cumulative, and that's why it's worth more. It requires that you remember more stuff. And I'll have these dates posted on our website, but tentatively I'm planning to have the 2 midterm exams at the end of each month, so at the end of January and the end of February, but that's subject to change. I'm going to be out of town at the end of this January. I'll be in Japan. I have to decide how to deal with that. Another part of your grade is going to be problem sets. You'll turn those in and they'll be graded. So you'll be turning those in on Wednesdays. And then discussion section participation. I want all of you to be ready to go to the board and draw reaction mechanisms and energy diagrams and all the stuff that you were exposed to back in Chemistry 201 that we're now going to use heavily in Chemistry 202. Okay, and then the final exam, that's set in stone because that's decided by the university. So as you may know, not everybody is here in class today. I had a flurry of emails from students, even from the TA. That's why Gene isn't here. So apparently there's some sort of thing called the Arctic vortex or the polar vortex that's making freezing cold temperatures that we don't have here in Southern California. But I don't know, you may know people that aren't here today in class. That means they're stuck because they couldn't get their flight out to California. Okay, so what are we doing this quarter? Let me start off by reminding you of what you did last quarter, because it's now sort of hazy and foggy because that was a month ago. So the syllabus from Chemistry 201 that Professor Jarvo sent me walks through this, the stuff that you were exposed to. So in Chemistry 201, back in the fall, you were exposed starting off to basic information about the shapes of orbitals and the consequences that they have for reactivity. And the important thing that you covered was frontier molecular orbital theory. And in the next lecture that I'm going to give you a review of frontier molecular orbital theory because it is so essential for our understanding of organic chemistry. You learned about stereoelectronic effects, conformational analysis, you had exposure to something called hard and soft acid-base theory, and then you got a tiny taste of elementary thermodynamics and kinetics. So reaction coordinate diagrams, we're going to use those more this quarter in connection with explaining kinetic phenomena. You learned about bond strengths and how to estimate enthalpies when reactions are favorable or unfavorable. And then you had a little bit on transition state theory and Hammond postulate. And if you didn't have those things, if the syllabus was wrong, just tell me and I'll recover that this quarter. Hopefully most of the class, or at least half of the class that you had, was on the connection between frontier orbitals and arrow pushing. And then I'll give you a quick review on that during the next lecture to make sure that we're all on the same page with that. So it would have been just a lot of arrow pushing where you did SN2 reactions, addition to carbonyls, carbocation chemistry, carbanions or lone pairs, and then a lot of pi orbital stuff, alkenes, enolates, enamines. That's really the basis for modern organic synthesis, is this part E stuff right here, and all the arrow pushing that you did associated with that. So this is almost all of the key stuff that you need to know to understand organic chemistry. There's one last part that you did not cover, and I'm going to finish that up before we start on to the main meat of this quarter. So I'll finish up the last part of sigma orbitals as nucleophiles so that you have a complete understanding of frontier orbitals and how they impact reactivity. So this is the start of Chemistry 202. And here's the rest of the stuff that we're going to do this quarter. This is the second quarter of organic reaction mechanisms. We're going to have a couple of lectures, 2 or 3, on third row atom chemistry. So hopefully you had some sort of introduction to the power of longer bonds. Organosilicon reactions on a lot of carbon-silicon chemistry. We're going to take a very particular look at organic reaction mechanisms and arrow-pushing mechanisms with respect to phosphorus chemistry and sulfur chemistry. You don't get enough of this, you don't get the correct mechanisms in sophomore organic chemistry. I'll give you the correct mechanisms and tell you how they relate to frontier orbitals and to stereoelectronic effects. We're going to spend a great deal of time talking about pericyclic reactions. Pericyclic reactions are all about what happens if a nucleophile attacks an electrophile and at the same time the electrophile comes back and attacks the nucleophile. There's this issue of concertedness, and I'll talk about 4 types of pericyclic reactions and give you a zillion examples and a zillion flavors of those. Then we're going to start talking about radical reactions. There's going to be a dramatic change in our thinking as we switch from regular arrow pushing to fishhook arrows or half-headed arrows. And then we'll try to finish off the class with, well, I'm not sure if we'll finish it off here, by talking about kinetics. And this is where we really get empowered with our thinking about organic chemistry. Can't emphasize enough that you will not have a complete understanding of organic chemistry or a complete control of your reactions until you start thinking in terms of concentrations. So this will be really essential, is to think of reactions in terms of reaction concentrations, and that means kinetics. So we'll talk about some various aspects of kinetics, and I certainly hope we'll have a chance to do a little bit of computational modeling, so it's not just all working out concentration dependence equations, regular kinetics equations. That's not the way that you need to think about organic chemistry when you're in the lab. And then finally, I hope somewhere in here, we'll have a chance to do some electronic structure calculations. So you'll see how easy it is to do. It's as easy as drawing in ChemDraw, and you get very powerful information about enthalpies that you can't get from bond strengths. I don't know if we'll have a chance to get to this. This is my first time to teach this class. I taught it, I say first time. I taught this 10 years ago, and I didn't cover the same set of topics because Chem 201 was organized differently. If we have a chance, I'll talk about electron transfer reductions and photochemistry as well. And a lot of you will find that you're doing if you've made a Grignard reagent, you're doing electron transfer reductions. Or Beauvau-Blanc react. There's a whole series of reactions that involve those mechanisms. And you need exposure to those to know how to handle those. Okay, so let's get started with the quarter. And I'll start off with a trivial reaction. What's the first reaction that you learn in sophomore organic chemistry? These are the first reactions that you learn. And at UCI, we teach the first quarter of organic chemistry. This is kind of the only chemistry, the only reactions you get to cover in that first quarter. So let's start off with a simple question here. And I will make all of these notes available online on our website, so you don't have to feel obligated to write everything down. You're free to do that. That's great. I want to start off with a simple question as we talk about this alkyl bromide. And that is that why is it that E2 elimination is favored over substitution? So why is that? And here's the mechanisms for these reactions. In order to generate this carbon-oxygen bond, you have to go through an SN2 reaction. Alkoxide attacks the carbon. But to explain this elimination product, instead we attack the proton, and then you end up with this process that generates a double bond. And so why is it that the alkene is favored over the ether?
Using a bulky base.
So bulk. So sterics would be the term. That's a great description. That's the answer that I would give. So we usually use, well, let me come back to this. So if we understand why the alkyl bromide gives that result, let me come back and ask this. If I change that to a tosylate, now look at the result. I haven't changed the alkyl group. That's the same in each case. But now look, it's the ether that's favored to a 99% extent. 99 to 1. Complete reversal of the selectivity. Right? The tosylate group is on the opposite side from where the nucleophile is coming in. This cannot be due to sterics. It can't possibly be due to sterics. There's no way. The bulky base or the bulky nucleophile is up here. The leaving group is down here. So there must be some deeper explanation that will allow us to explain the simplest of all kinds of reactions, which seems to be kind of perplexing, right? There must be something deeper to organic chemistry that they never talked about in chemistry, in sophomore organic chemistry, and we need to talk about that more. You got an introduction to that last quarter. We're going to continue to talk about that. Okay, so what is it that allows us to predict the results correctly instead of incorrectly? And explain the results of organic chemical reactions. If you want to explain organic chemistry, right, we can't just look at things like sterics. There must be something deeper for us to think about. So if you go back to general chemistry that you took as a freshman, in general chemistry, they taught you how to think about the interactions of molecules. They gave you a very simple equation when they said, if you want to think about the interaction between any two molecules, two methanes, why do methane molecules attract? Why is methane a liquid? There's no hydrogen bonding. Why does helium form a liquid? There must be some interaction there. And in general chemistry, you learned about this set of interactions. You learned about Van der Waals interactions, this completely empirical understanding of what makes molecules attractive to each other. And you learned about charge. That's Coulomb's law. Actually, you probably learned about that in a physics class, but it applies to chemistry as well. And if you look at all of physical chemistry and biology, this is the equation they're using to explain the interaction of molecules. These Van der Waals interactions and charge interactions. And the importance here is all three of these terms embedded in here are distance-dependent terms. The Van der Waals interaction is explained by something called a 612 potential. That as two molecules get closer and closer and closer, and as the distance shrinks, there's this 12th order dependence that makes it really hard to push two molecules together. But as you're farther away, for example, with two methane molecules, there's something attractive. And it operates over with a different distance dependence, a 6th order dependence that makes even methane molecules want to be close to each other. So this is a powerful way to explain, for example, the interaction of proteins, the folding of proteins, basically anything that doesn't involve the formation of a bond. And so the problem is when you go from general chemistry to sophomore organic chemistry, suddenly you're interested in the formation of bonds, and this equation no longer works. This equation is a complete failure. And there's another equation that you should have been introduced to, but you probably weren't, that would help you to understand organic chemical reactions. And so let's look at this dramatically different equation that organic chemists should use. And it looks stunningly familiar, I hope. It looks very familiar. This is the way you should think about the formation of bonds when two reactants come together. In organic chemistry, if we want to explain the difference between this transition state where we attack carbon and this transition state where we attack a proton, we also think about this in terms of three distance dependence effects. So let's take a look at this equation that you should be using somehow in your mind to think about the interaction of molecules. So if I want to think about the interaction energy between two molecules when they get closer and closer and closer, and compare the energies of this transition state with that transition state, I need to keep in mind something that's distant dependent that's repulsive. We call that sterics. That's a very easy concept to understand. Right? If I take a hammer and I hit the table, it doesn't go through the table. That's sterics. That's a way of thinking about that. But there's this other thing that we often invoke called electronics. Whenever we can't explain things based on sterics, we usually say, oh, it's electronics. And this is really underselling the power of organic chemistry. If we group everything else into electronics, everything that's not sterics. So in fact, this thing that organic chemists refer to as electronics is actually composed of two different terms. When two molecules come together and start forming a bond, this is what's coming into play. There's this very complex equation here that's got a distance dependence. And you can't see the distance dependence in here. There's no distance number r in this denominator here. It's actually embedded here in this beta value. That's called orbital overlap. When orbitals overlap, there's a distance dependence to that, how close they are in space, how they're orienting with respect to each other. And then this last part is exactly the same as the equation you used in freshman chemistry and in physics. It's Coulomb's law. So two of these are totally obvious, sterics and charge. Totally obvious. You talked about those things in general chemistry. It's this last part that really is confusing and actually is the most powerful. And this, it turns out, is arrow pushing. So you should now think about every single reaction that you draw on a piece of paper in terms of sterics. I'll ask you to explain the results of reactions. And I'll expect you to invoke either sterics or charge or this other mysterious thing that we called arrow pushing. Now last quarter you were introduced to something called hard-soft acid-base theory. It's in Fleming, and in my experience that does nothing but leave everybody in a state of confusion. Hard and, right, what does hard mean? How can an atom be hard or an atom be soft? Atoms are not hard and soft, and that's just a lame way to explain things. That's the reason people invoke hard and soft acid-base theory, is they're trying to somehow tease apart electronics into these terms without actually telling you, well, there's two separate terms here. They just don't want to tell you that. And I'm just telling you simply, explain your reactions in terms of these three things when I ask you to explain things. So this seems so new and exciting to us. You got introduced to this in the last quarter. Let's continue talking about this. This is what really empowers the formation of bonds. That's arrow pushing. And I'm going to come back to the history of arrow pushing. Where did that come from? It's almost 100 years old now. It was first introduced by Robinson and Lapworth in this paper down here in the Journal of Chemical Society. And they point out, they say, similarly, the conjugation of three double bonds, supposing such to occur, would be represented thus. They were trying to explain resonance effects. And for the next 90 years, this arrow pushing turned out to be very powerful for explaining resonance and chemical reactions that form bonds. Very powerful stuff. It was widely adopted. It is still widely used today, universally used. The problem with Robinson and Lapworth here is they never set down clear rules. They never said exactly what arrow pushing was supposed to be about. And so people started to use it for all kinds of different things. It's like, well, arrow pushing's powerful. Let's use it for anything we want. And so for the next 80 years, maybe 70 years, people were using arrows to represent interaction of charges, sterics, atoms flying off, and the literature is full of this. If you go to the literature and you try to decide what the mechanism is, you'll get 5 different mechanisms, the arrows going in 5 different ways. So it wasn't until 1976, there was a book by Ian Fleming. This is the book that I'm recommending that you use for this class. Hopefully you all have looked at this or have a copy. But there's an earlier edition of this book that you may not be familiar with. It's the edition of the book that I got trained off of and all the other faculty members got trained off of. This is the earlier version of Fleming's book, published in 1976, and he makes a seismic statement in that book. A landmark statement hidden on page 63 or somewhere deep inside that book that totally changes the way you should think about organic chemistry, that makes it fit with this 3-part equation that I just showed you. And what he says is and he was trying to explain electrophilic aromatic substitution, but one of his sentences is, curly arrows, when used with a molecular description of bonding, work as well as they do simply because they illustrate the electron distribution in the frontier orbital. And for reaction kinetics, it is the frontier orbital that is most important. What he's saying is if you care about which reactions are fast and which reactions are slow, if you care about are you going to get byproducts or the product you want, if you care about whether you're going to get out of the lab at 3 o'clock in the afternoon or 3 o'clock in the morning, if you care about the speed of reactions, then what you should do is you should be caring about the electron distribution in the frontier orbitals. And curly arrows work if and only if you use them to represent the interaction of filled orbitals with unfilled orbitals. He's telling you how you should use arrows. You should use them to represent the interaction of filled orbitals. So when you draw this is what we're going to be doing this quarter. We're going to be doing arrow pushing just like you've continued to do. But the reason why this works well is because it represents the interaction of some pi-like orbital that's filled with some sort of an antibonding sigma star-like orbital. One of the 6 types of canonical orbitals. That's when it works well. And when you start to use it for other things, it will stop working well. And so I'm going to push you this quarter to make sure, just like in Chem 201, that you continue to use your arrow pushing to represent this, not other stuff. And whenever you need to, you can fall back on the fact that this stuff, which represents this, is backed up by a fundamental quantum mechanical equation. Arrow pushing is very powerful because it represents a quantum mechanical interaction of filled orbitals with unfilled orbitals. Very powerful stuff. So all those orbital interaction diagrams that you were exposed to are quantifiable with this equation. And let's take a look at what this equation says. This equation says that there's some sort of a coefficient that describes the size of the orbitals on each of these atoms. So you learned about Huckel theory last quarter. That's what this is. These are coefficients. And this beta value tells you how much they're overlapping with each other. Right? I want this orbital here on this sigma star orbital to overlap with the filled part, the big part of this filled orbital. That's what that beta coefficient says. It says overlap. And then you look down at the bottom, right? I hate looking at equations like this. The math is so complex, but even I can handle this. And this tells us that it really matters the energies of these orbitals. And that's not something that's represented on a diagram like this. Some orbitals are very high in energy, very nucleophilic, and some electrophilic orbitals are low in energy, very easy to put electrons into those. And so you want nucleophiles to have high orbitals, and you want electrophiles to have low orbitals so that the gap, the difference between those is small. And when that gap is small, when this gap is small, this becomes very big and powerful. You form a lot of bond, you get a lot of bonding energy out. Okay, so we're not going to look at that equation anymore. It's kind of hard for us to look at. What I want you to do is think about this stuff. But this is always there for you when you need it to empower your thinking about organic chemistry. Okay, so let me come back to this very simple way of looking at organic chemistry that's very powerful. So whenever you think about the interaction between two molecules, is it favorable or is it unfavorable? Is it fast or is it slow? You can quantify that, or at least kind of empirically quantify that by thinking about three different things: sterics, orbital interactions, and charge. And so what we said, what Fleming said in 1976, is that if you really want arrow pushing to be powerful, you should use it to represent this. So the problem is that charge is important in organic chemistry. And so you will have the tendency to want to use arrows to represent the interaction of charges. And so what's wrong with that? It works. And you can go to journal article after journal article and find examples where they push arrows from negative charges to positive charges. It is definitely true that charge is what makes this oxygen, or an important factor, and what makes an oxygen alkoxide or carboxylate group attracted to this carbocation center. No doubt that that's important. And it actually works here to explain, oh, you form a bond there between oxygen and the carbon atom of this trityl cation. But the problem is, once you get used to drawing charges, interaction with charges, and using curved arrows to do that, once you start down that dark side or the dark path, the problem is you're going to run into case after case where this fails. So this works half of the time. The other half of the time it fails badly. And that's not where you want to put your money. So, right, if I ask you where a hydroxide ion will attack this oxocarbenium ion, this oxonium ion, I promise you it will not ever attack on the oxygen. Right? Even though that's where the positive charge is, and you know that already. And you might invent some weird rule that tells you, well, there's an exception here. You have to draw a resonance structure. And right? If you have to memorize all these exceptions, then that's not a very good rule. Right? Once you start making charges attack charges, do you really want to form a bond between boron and carbon? Is that really where you want to? No, that's not where you want to form the bond. And in freshman chemistry, you learn that hydroxide reacts with hydronium ions. It does not form oxygen-oxygen bonds. That's not the way that chemistry works. And if you take an aminium ions don't react on nitrogen. You're going to badly violate the octet rule if you attach this oxygen to that nitrogen atom. Nothing good can come out of that. So we have to just have a general agreement that we're going to use arrow pushing to represent the interaction of orbitals. And that's not to say that charge is not important, but if you want to imagine the importance of charge, just draw the charges. You don't have to draw arrows between them to understand that minus is attracted to plus, or that like charges repel. That should be totally obvious to you. Opposites attract each other, and familiarity breeds contempt. So charges are totally obvious. We don't need arrow pushing to represent charges. Okay, so why does this charge stuff, why does using arrows to represent the interaction of charges fail so badly? Half of the time. Why does that happen? And the problem has to do with Lewis structures. In freshman chemistry, you learn to draw Lewis structures for simple organic molecules. You continue to do that in sophomore organic chemistry, and I adamantly want you to continue to draw correct Lewis structures. If you can't draw correct Lewis structures, everything is over. The problem with correct Lewis structures, the Lewis formalism, is that it often misrepresents the charge distribution in organic molecules. So let's talk about that. If I take this tetramethylammonium ion and I interact it with some strongly reactive nucleophilic basic molecule, like an amide anion. Right? Even though I draw the positive charge here, I draw the negative charge there, if I try to make a nitrogen-nitrogen bond by attacking there, right, again, that's a violation of the octet rule. That won't work. That'll be completely bad. And so why is this such a failure at explaining what's going on? Not only does it not recognize the octet rule, but if you take an amide anion and react it with a tetramethylammonium ion, it doesn't attack nitrogen. Where does it attack? In fact, it will pull off a proton from one of these carbon atoms. That's what an amide anion will do. That's what hydroxide anion would do most of the time. But it depends on what kind of nucleophile or reactive species that you use. If you take a phosphine, a very nucleophilic phosphine, like trimethylphosphine, and you add it in there, it doesn't pull protons off anymore. Trimethylphosphine will do an SN2 reaction and attack a methyl and displace trimethylamine as a leaving group. Completely different patterns of reactivity. And so why is it that this fails so badly, this charge interaction, using arrows to draw the interaction of charges? It's because the Lewis structure formalism here misrepresents the nitrogen as the center of positive charge. If I ask you what's the most electronegative atom in here, nobody is going to say carbon. And nobody is going to say proton. Nitrogen is the most electronegative atom. And if you look at the actual distribution, or a better representation of the distribution of charges, you can get that in 1 second from an ab initio calculation. It tells you that, in fact, the positive charge is mainly associated with those protons. And that's why bases or nucleophiles with a high concentration of charge, of negative charge, prefer to attack the protons. That's where most of the positive charge is. And you can't get that from a Lewis structure. You have to look at 5 or 10 examples to become familiar with this idea. Protons are where the positive charge is, not nitrogen. Nitrogen's electronegative, right? And you can see that here in this, from these computed charges, nitrogen's electronegative. It's not so obvious that carbon would have a partial negative charge, right? So phosphine actually attacks carbon because it's not dominated by charge. That's dominated by HOMO-LUMO interactions, by interactions of the filled orbital here. It's a non-bonding lone pair-like orbital with the sigma star orbital for that carbon-nitrogen bond. Charge plays very little role for that trimethylphosphine reaction. Okay, so charges don't form bonds. Electrons form bonds. And so we're going to use curved arrows to represent the interaction of filled orbitals with unfilled orbitals, not the interaction of plus charges with minus charges. Okay, so if you type in the word mechanism on the web and some reaction name, the Riley-Hickenbottom reaction, Eschen-Moser fragmentation, there's all kinds of reactions. You'll come up with all kinds of answers for what is the mechanism for the reaction. And unfortunately, there is no agreement on what is the meaning of the word mechanism. And I'm going to ask you questions on the exams and on the problem sets where I ask you what is the mechanism, and I'll try to be clear about what I'm asking for, but let me show you what I mean. If I go out and ask 10 chemists what is the mechanism for this interesting reaction, and no doubt this reaction is very interesting. You take this long chain attached to a furan, there's an epoxide at one end, and I add a Lewis acid catalyst. It doesn't have to be indium tribromide, it could be any Lewis acid catalyst. And what I'll find is I start to get ring-like compounds. This particular catalyst, Lewis acid, just happened to give a decent yield. It's 3 new rings, 5 stereogenic centers when there was only 1 before. Something very powerful is happening here. So this is clearly an interesting reaction. And if you're interested in building molecules and using organic synthesis, you'd like to know more about this and how to harness these types of processes. But if I go and ask a kineticist or a physical organic chemist what's the mechanism for this, they might give me this. There, I'm done. And if I ask you what's the mechanism for this, and state it so simply, and you gave me that, I can't say that you're wrong. That's actually correct. That's the mechanism for this reaction. What this says is that the rate of this reaction is dependent on the concentrations of 2 things. It's dependent on the concentration of the Lewis acid that you put in there, and it is dependent on the concentration of the substrate. And I hope that that is absolutely obvious to you. If I add 10 times more Lewis acid, doesn't it make sense that it ought to be 10 times faster? Right? If you want to have your reaction done by lunchtime instead of the next day, put in 10 times more of the reagent if you think the concentration dependence is first order. That's a simple way to improve your productivity in the lab. If you had 10 times more of the substrate, of course you'll form product 10 times faster. That doesn't mean the yield is higher, but it means you'll form the product in a molar per second rate, you'll form it faster. Okay, the power of this description is that it gives you a way of thinking about competing processes. That's why this description is powerful. So let me show you what's embedded in here that's actually a powerful way of thinking about organic chemistry, and you can use that. What this is telling you is that there's this dependence. Initially, there's this equilibrium between these two species. As the lone pairs on this oxygen attack the Lewis acid, you'll form this Lewis acid complex here, this ylidic-like complex. And then this has two choices. One choice is to go back to the starting materials and release the Lewis acid. So there's a pre-equilibrium here. If the equilibrium is favored by a factor of 10 times higher, you'll form product 10 times faster. If you use a Lewis acid that is too weak and never coordinates and stays on this side, you won't get product formation very quickly. So understanding the direction of this equilibrium, does it favor this side or does it favor this side, can tell you how fast you're going to form product. But there's something more that's embedded here, and that is that there's this key step that occurs, something called the rate determining step. This is the slow step for the reaction. And in this slow step, this somehow goes to product. And the important thing that we need to look at here is these two numbers. The rate at which this goes back and releases the Lewis acid, and the rate at which this somehow forms all of these rings and does something interesting. Because when I look at these two numbers here, if somebody told me that this is 1 and this is 10, that tells me that for every one of these complexes it has a choice. And 10 times out of 11 it's going backwards and releasing, and only 1 out of those 11 times is it going forward to product. And that's the kind of thinking that will help you think about organic chemistry, is thinking in ratios. 10 to 1. How often does this thing go back or go forward to product as opposed to releasing Lewis acid? Is it 1 out of every 10 times? 1 to 1 ratio of times? 99 out of 100 times? These two numbers here, these rate constants, tell us about those choices that this reactive intermediate has. And when we start talking about kinetics in detail, that's the kind of thinking I want you to bring to the table when we think about reactions. Thinking about reaction choices in terms of ratios. And this will be particularly important when you think about side reactions. So this isn't very satisfying, actually, to me as an organic chemist. I mean, I do love thinking about these ratios and these numbers. The problem is that the steps that occur after the rate determining step, right? It's rate determining because it's the slowest step. All the steps after this occur faster than the rate determining step. And unfortunately, these steps that occur after this rate determining step sometimes are really interesting. So if I ask somebody, what's an arrow pushing mechanism for this reaction? In other words, I'm being very particular. I don't want to see that kinetic equation. When I ask you, suggest a plausible arrow pushing mechanism for the following reaction, I expect you to draw out something much more elaborate. So what is an arrow pushing mechanism? An arrow pushing mechanism has every single Lewis structure drawn out for all of the reaction intermediates. And every single step is an elementary reaction step. That's an arrow pushing mechanism. It means you've broken it down into every single elementary step. And I know what an elementary step is, and I can check that using computational calculations. An elementary step is characterized by having a single transition state. So the goal of an arrow pushing mechanism is to break down a reaction into a series of elementary reaction steps, each of which has a single transition state. And as soon as you do that, you can now think about transition states. You can draw transition states into computers and calculate their energies. You can look at orbital interactions in the transition states. If you don't break reactions down or mechanisms down into elementary reactions, you won't be able to think about transition states. Okay, so here's the way, if I ask for an arrow pushing mechanism, I might envision this to occur. There's some sort of a coordination between the lone pair and some unfilled orbital on the indium. You form this Lewis acid complex that makes the sigma star orbital here very easy to attack. And now I have these pi-like orbitals, and I might not be sure about the mechanism after this. One possibility is that all of this happens in a concerted fashion. This pi bond attacks that antibonding orbital, and at the same time this pi bond comes over here and attacks that developing carbocation. And simultaneously this electron-rich furan comes in and attacks that carbocation as it is forming. So one possibility is that this is all a concerted reaction mechanism. And then finally, this is kind of like the last step in an electrophilic aromatic substitution. You simply pull off the proton by attacking some sort of an anti-bonding orbital here between H and carbon. But there's also another possibility here. And that possibility is that maybe this is stepwise. Maybe there's an initial opening to form a carbocation and you simply attack that. And these are not at all engaged. This double bond isn't engaged and that double bond in that first step. That's one possibility. Maybe these other steps are fast, and this is the slow step in the reaction. Maybe you form a true carbocation here, and then this double bond comes around and attacks that carbocation to form a new carbocation. And then in another step, with an individual transition state, maybe finally this furan comes around and attacks. So these are all different possibilities. Or maybe the first two rings form simultaneously, like this. Or maybe just the first ring. We don't know. You have to do some experiments to distinguish between these mechanistic possibilities. And that's really interesting. And in fact, people have done those experiments. So for example, what they have shown is that this is the rate determining step for the reaction. And if you add electron donor groups here, this gets faster. If you make this more electron rich, product formation gets faster. And what that shows you, what that tells you, is that this ring is somehow involved in this key bond forming step that forms that first bond. You can't use that to, if I don't have this interacting with that unfilled orbital over here, I can't explain why an electron donor group would make this bond formation faster. That shows that this is the likely mechanism for this reaction, this concerted process here, where all of these things are now happening simultaneously. So we'll talk more about those kinds of kinetic tools later, because they help you sort out all of the possible mechanisms for a reaction. Okay, so in Chemistry 202, what are we going to do? We're going to talk more about what does it mean for a reaction to be concerted or stepwise. This is pericyclic reactions. There's a certain set of reactions that have a set of very special properties that allow them to be concerted and easily concerted. Here it wasn't so obvious, but there will be cases where it's totally obvious just from looking at the reactions that they ought to be concerted. So we're going to think about what makes a reaction not concerted versus concerted, and in particular pericyclic. And then we're also going to think about the concentration dependence of these. This idea that if I have 10 times more of the Lewis acid, that I can make the reaction 10 times faster. Or this idea that maybe you get to this intermediate and it has two choices. Maybe it does an elimination here to give you a byproduct, or maybe it goes forward. Those choices, 10-to-1 ratio, 1-to-1 ratio, determine how much byproduct you get versus product that you want. And that's what you care about when you walk into the lab. How much product do I get versus how much product don't I get? The reason why this is only 37% yield, I didn't draw the product here, is because there were side reactions. There's other things that can happen, and you want to think about those choices of each of your reaction intermediates. Okay, so that's all for today. When we come back on Wednesday, I'm going to reintroduce you to orbitals and how to think about them, because the rest of the quarter we're going to spend our time analyzing these kinds of interactions in terms of canonical filled orbitals and their interaction with unfilled orbitals.